Today we're going to do an example where we find the general solution to this inhomogeneous linear ordinary differential equation with constant coefficients. Y double prime minus 3y prime minus 4y equals 10 sine 2x. Our plan for doing this is to first find the complementary function y sub c. That's just the general solution to the associated homogeneous problem. So that's the same left-hand side, but we make the right-hand side 0. That's how we find y sub c. Then we'll find y sub p, a particular solution to the inhomogeneous problem, so this problem here. We'll use annihilators to do that, and then lastly, we'll write down our general solution, which is just the sum of the two functions that we find in steps 1 and 2. So let's get started with step 1, find y sub c. Okay, so the associated homogeneous problem is y double prime minus 3y prime minus 4y equals 0. Okay, so we first solve the problem where we don't have anything on the right-hand side. All right. So to do that, we need to write down the auxiliary polynomial. So I'm going to write down our equation in operator notation. So that's going to give me d squared minus 3d minus 4 applied to y equals 0. Okay, so remember that capital D is our differential operator. It's representing the derivatives. So I have d squared to represent 2 derivatives, d to represent 1 derivative, and then no d here because there's no derivative on this last term. Okay, so this tells me that my polynomial p of r is r squared minus 3r minus 4. And we want to find the roots of this polynomial, so I'm going to factor it to get r minus 4 times r plus 1 equals 0. That tells me that the roots are 4 and negative 1. I'll go ahead and move this to the side. The roots of that polynomial are telling me what to put in the exponents of my general solution. So my general solution to the homogeneous problem, or y sub c of x, is c1 e to the negative x, so that's from this negative 1 here, plus c2 e to the 4x. That's from this 4 here. All right, so we're going to just kind of press pause on this. We're going to keep this in mind for later. We're going to move on to step 2. So step 2 is find a particular solution. So to do that, we're going to look at the right-hand side. And look at the right-hand side of our ODE. I'm going to call this f of x, capital F of x here, and that's just 10 sine 2x. Okay. Now we need to determine an annihilator, and that's an operator that when applied to this function f of x, we get 0. So determine an annihilator, which I'll call capital A of d, and apply it to the ODE. The original ODE in that case. The way we determine an annihilator is to really look at, for a sine or a cosine function, we want to look at what's multiplying x inside that function. Here we have a 2, and we want to think about what operator, if I was solving a homogeneous differential equation, what polynomial differential operator would lead me to get a solution of this form, sine 2x. We don't really need to worry about the 10 here. I just want to focus on how would I have gotten sine 2x. Well, it would have been an operator that would result in an auxiliary polynomial that had roots r equals 0 plus or minus 2i. So if I had the roots plus or minus 2i for my auxiliary polynomial, then I would have written down a solution of the form sine 2x. So that tells me that my annihilator, a of d, should be the operator that has associated polynomial with these roots. So this is going to be d squared plus 4. Right? I chose that because if I had written r squared plus 4, which is the polynomial associated with this operator, the roots would have been plus or minus the square root of negative 4. And plus or minus the square root of negative 4 is plus or minus 2i. All right, So we apply this operator, this annihilator, to our original ODE. And I'm going to do this all in operator notation. Before I do that, I'm going to just remind you really quickly that this operator for our original problem, I can factor it as d minus 4 d plus 1 applied to y. So that's what I'm going to use when I apply this operator, d squared plus 4. So I'll apply d squared plus 4 to my original ODE. So the operator for that, for my original problem, is d minus 4 d plus 1 applied to y. And if I'm applying this to the original problem, the reason we chose a of d in this form is so that when I apply it to this right-hand side, I get 0. That's why it's called an annihilator for that function. So on the right-hand side now, I can say this is 0. Okay, now I have this new homogeneous differential equation, and I can solve homogeneous differential equations. So let's write down the general solution to this new problem. To do that, I would need the auxiliary polynomial, which is r squared plus 4 times r minus 4 times r plus 1. The roots of this polynomial, are r equals -1, 4, and plus or minus 2i. So we get the same roots that we started with in our homogeneous problem. Remember, we had 4 and -1. But we also pick up new roots from the annihilator operator, plus or minus 2i. So the general solution to this problem is y equals c1 e to the negative x plus c2 e to the 4x. And now I need to write down the general solution associated with these roots, plus or minus 2i. So that's going to give me c3 cosine 2x plus c4 sine 2x. All right. So let's look at this solution here. Notice that this portion of the general solution matches the terms in the complementary function. So we don't want to use these terms in our trial solution. Instead, we want to use the new terms that we've picked up. So these terms here, these cosine and sine terms, these are going to form our trial solution. So I'll write the trial solution up here because I'm going to run out of room. Our trial solution is y sub p equals some constant, I'll call it capital A. You can call it C3 if you want and C4 for the other term, but I'm just going to call it capital A for a constant, cosine 2x plus b times sine 2x. This is our trial solution. We are going to substitute this into our original ODE and figure out what these constants a and b need to be in order for this to be a particular solution. All right, so I have got here our original ODE, our complementary function, so the solution to the homogeneous problem, and a particular solution, or at least the form of the particular solution. This is our trial solution, and we want to plug this in to our original ODE, and that'll tell us what the constants a and b need to be. So that's our plan here. So let's go ahead and do that. In order to substitute this function into this ODE, I'm going to need a first derivative and a second derivative. So I'm going to go ahead and take those derivatives. I'll just write down really quickly. Y sub p is a cosine 2x plus b sine 2x. The first derivative of that function is going to be negative 2a sine 2x plus 2b cosine 2x. And the second derivative is going to be negative 4a cosine 2x minus 4b sine 2x. So I'm going to go ahead and substitute these expressions in to this ODE. So I'll have negative 4a cosine 2x minus 4b sine 2x. That's my y double prime. minus 3 times y prime, which is negative 2a sine 2x, plus 2b cosine 2x, minus 4 times y, and that's just y sub p here is cosine, a times cosine 2x, plus b sine 2x, and I'm setting that equal to the right-hand side, which is 10 sine 2x. All right, so just to recap, this portion here is y double prime, this portion here is minus 3y prime, this portion here is minus 4y. So you can see it is the left-hand side of my original ODE, and I've substituted in y sub p. All right, so now the plan is to combine like terms. So let's combine like terms. So I'm going to group all the terms that have cosine next to them, and then I'll group all the terms that have sine next to them. And if you do that, you'll get negative 8a minus 6b cosine 2x plus 6a minus 8b sine 2x, and that's equal to 10 sine 2x. Okay, so now we want this equation to be satisfied. We need to choose a and b so that this all works out. And the way to do that is to equate coefficients on the cosine terms on the left and the cosine terms on the right, which don't exist, the sine terms on the left and the sine terms on the right. So if you notice, we've got, let me get a highlighter here, we've got 6a minus 8b sine 2x on the left, and we have a 10 sine x on the right, sine 2x on the right. So that means one of the equations we'll need to satisfy is 6a minus 8b equals 10. We have another equation that we'll need to satisfy as well, because we have negative 8a plus 6b cosine 2x, and there's no cosine terms on the right-hand side. You could think of this as plus 0 cosine 2x. So really, we need to match negative 8a minus 6b. We need to set that equal to 0. So negative 8a minus 6b equals 0. Now if you solve this system of equations, you'll get that a equals 3/5 and b equals negative 4/5. So looking back at our particular solution here, here's a and b. We just found values for those constants. So I'm going to write down our particular solution is equal to a times cosine 2x, a is 3/5, plus b times sine 2x, and b is negative 4/5, so I'm going to go ahead and write minus 4/5 sine 2x. That is our particular solution to the inhomogeneous problem. So now we've got our complementary function, or the solution to the associated homogeneous problem, and we've got a particular solution. The general solution will just be the sum of those two functions. So let's scroll down here. Okay. So again, let me make sure this is in a good spot. There we go. So we've got our original ODE, our complementary function, and our particular solution. So step 3 of our plan was just to write down the general solution. So the general solution to the inhomogeneous problem is y of x equals, and it's just the sum of y sub c plus y sub p. So c1 e to the negative x plus c2 e to the 4x plus 3/5 cosine 2x minus 4/5 sine 2x. This is our general solution to the inhomogeneous problem.